A Chinese space rover spotted a mystery hut. They built a base on the dark side of the moon.
In my opinion, that is not a natural structure. It's got to be some intelligent species that created it.
Beneath the moon's serene, cratered face lies a realm humanity has never truly touched, the far side. In 2024, China's Chang'e 6 mission shattered that isolation, returning the first ever samples from this hidden world.
China's Chang'e 6 lunar probe's on its way back to Earth after collecting rock and soil samples from the far side of the moon.
What scientists uncovered in the South Pole Aitken Basin was proof that the moon's far side is not a dead, frozen relic as we long assumed. Today, we'll unveil how China discovered something mysterious on the far side of the moon. The far side awakens. In June 2024, humanity finally set foot on the part of the moon that had remained a mystery for billions of years, the far side. The Chang'e 6 mission, a daring feat of engineering and ambition by China's lunar program, returned nearly 2 kilograms of pristine lunar soil from this hidden hemisphere, making history in a way that no previous mission had.
Chang'e 6 module landed on Saturday in a volcanic basin close to the moon's south pole and has collected samples of rock and soil.
For decades, all our samples, Apollo's 6 landings, the Soviet lunar missions, even China's own Chang'e 5, had come from the moon's near side. Scientists had pieced together their models of lunar formation, volcanic activity, and chemical composition entirely from a single Earth-facing vantage point. It was like trying to understand the Amazon rainforest by sampling only a handful of trees along a single riverbank. The far side, almost completely obscured from Earth, had been off limits. This is an entire hemisphere, locked away by physics. But now, the secrets have been unlocked. The target for Chang'e 6 was audacious. The South Pole Aitken Basin, a colossal scar stretching roughly 2,500 kilometers across and plunging deep into the lunar crust. This basin is not only one of the largest impact structures in the solar system, but also one of the oldest, formed during a cataclysmic collision billions of years ago. Scientists have long suspected that the impact that created the basin punched through the moon's crust and exposed deeper mantle material. If true, rocks from this region could be a window into the moon's inner workings, offering clues about its formation, its evolution, and even the dynamics of the early Earth-Moon system. However, landing on the far side presented an entirely new set of challenges. Unlike the near side, the far side never faces Earth. A lander there loses radio contact the instant it passes out of line of sight, making remote operation nearly impossible with conventional methods. China's engineers solved this with an elegant solution, the Queqiao relay satellite. Positioned in a halo orbit around the moon, Queqiao acted as a communications mirror, simultaneously seeing both the lander on the far side and the ground stations back on Earth. This allowed Chang'e 6 to operate with split-second precision, sending commands, receiving telemetry, and executing a complex series of maneuvers entirely through the satellite link. Without it, the mission would have ended before it even began. On the surface, the expectations were clear. The far side is fundamentally different from the near side. While the familiar lunar man-in-the-moon patterns of dark basaltic plains, the Maria, dominate the near hemisphere, the far side is almost entirely rugged highlands and impact craters, a landscape sculpted by relentless bombardment over eons. The crust here is significantly thicker, in some areas dozens of kilometers more than the near side, and lacks the heat-producing radioactive elements concentrated in the creep-rich regions of the near side. Conventional models suggested that, without this internal heater, the far side should have gone geologically silent far earlier, its magma frozen, its surface locked in a dead, brittle crust. In other words, this was supposed to be the moon's graveyard. Yet, the samples told a different story. Chang'e 6 spent 2 days on the surface, scooping and drilling, carefully collecting both regolith and subsurface cores. When the return capsule landed safely in Inner Mongolia, for the first time, we had physical evidence from the hemisphere that had eluded observation for more than half a century. Even at first glance, the rocks were remarkable. The basalt fragments hinted at volcanic activity far more recent than anyone expected, challenging the long-held view that the far side had been inert for billions of years. Their composition revealed subtle differences from near-side basalts, including variations in trace elements and isotopic ratios, hinting at a complex mantle history and suggesting that heat was circulating through the lunar interior in ways models had not predicted. The samples also contained clues about the Moon's early bombardment history, the mixing of deep and shallow crustal material, and the processes that allowed the lunar surface to remain chemically active over geological time. The far side is now thought of as a frontier, rich in history, complex in geology, and full of surprises. And if Chang'e 6 is any indication, the secrets it holds are only the beginning. And what are those secrets? Volcanoes that shouldn't exist. When the first analysis of the Chang'e 6 far side samples hit the lab benches in 2025, the excitement went off the roof. Using high-precision isotopic clocks, researchers measured the decay of uranium to lead, samarium to neodymium, and other parent-daughter isotope systems embedded deep in the mineral grains.
These new findings were achieved through multiple approaches by scientists from this research institute.
The verdict was astonishing. These basalts had solidified only about 2.8 billion years ago. To the layperson, that might sound ancient, but in lunar terms, it was nearly contemporary. The prevailing model held that the Moon's far side had long since gone cold. Without the creep-rich regions, zones abundant in potassium, rare earth elements, and phosphorus, the far side lacked the internal radioactive heaters that prolonged volcanic activity on the near side. The creep signature, concentrated in areas like the Procelarum creep terrain, had explained why Maria on the near hemisphere erupted episodically well into the Moon's middle age, some as recently as 2 billion years ago. By contrast, the thick crust of the far side, often tens of kilometers thicker than the near side, was thought to act like an impenetrable lid over a cold, solid mantle. Magma simply could not form or, if it did, could not rise through the dense rock. And yet here it was, evidence of volcanic activity where none should have existed. The 2.8 billion year date contradicted decades of thermal modeling. It implied that the far side's mantle was not just molten briefly after the Moon's formation. It had stayed geologically alive for hundreds of millions of years longer than predicted. The implications rippled through the planetary science community. If the thick far side crust had not shut down mantle activity, what mechanism had kept it hot? Had heat been redistributed in ways models failed to capture? Or had previously underestimated radioactive or tidal processes played a role? This wasn't merely a minor adjustment to the lunar timeline. It demanded a full re-evaluation of the Moon's thermal evolution. The far side, long considered a static, unchanging landscape of craters and highlands, had a dynamic interior. Geophysicists began running new convection models, exploring how heat might circulate through a mantle insulated by a thicker crust. Some hypotheses suggested episodic overturns, with pockets of molten material rising over time, while others pointed to latent heat retained in localized mantle plumes. The 2.8 billion year eruption date from the South Pole Aitken Basin now anchors these theories, forcing scientists to reconcile the apparent contradiction. How could the Moon's internal engine operate under such seemingly prohibitive conditions? The rocks themselves added nuance to the story. Trace element analysis revealed subtle variations in iron, magnesium, and titanium concentrations, distinct from near-side basalts. These compositional differences hint that the far side mantle evolved independently, influenced by local dynamics rather than a uniform global cooling trend. In other words, the Moon's internal processes were heterogeneous. Its history is more complex than a simple cooling ball of rock narrative. The far side had its own volcanic chapter, written long after the near side's thermal stories had played out. For the scientific community, the ramifications went beyond lunar history. If a small, airless body like the Moon could maintain mantle activity for so long, models of thermal evolution for other planetary bodies might require revision. The assumption that small worlds lose heat rapidly, becoming inert within a few 100 million years, was suddenly too simplistic. Chang'e 6's samples also raised questions about the triggers of lunar volcanism. On the Moon, with no active tectonics and far fewer volatiles, what had driven far-side eruptions nearly 2.8 billion years ago? Some scientists now consider the possibility of residual heat from radioactive decay diffusing through the mantle over time, combined with localized mantle upwellings, providing enough pressure to breach the thick crust. Others propose that tidal flexing from Earth's gravity could have contributed energy to sustain pockets of magma. But that's not all. Water hiding in plain sight. The lunar samples also housed tiny glass spheres, barely a millimeter across, formed when micrometeoroids slammed into the Moon's airless surface at speeds exceeding 20 kilometers per second. The impact flashes instantaneously melted the local silicate dust, and as the molten droplets cooled mid-air, they solidified into perfect, microscopic orbs. Scientists had seen these beads before, but the Chinese team took a new approach. Instead of treating them as inert curiosities, they examined their chemical interactions with the solar wind. The sun constantly bombards the lunar surface with a stream of charged particles, mostly protons, the nuclei of hydrogen atoms. On Earth, our magnetic field shields us from this torrent, but the Moon bears the full brunt. When these hydrogen ions strike the surface, the glass beads act like sponges. Their silicate minerals are rich in oxygen, and the incoming hydrogen penetrates the bead's outer layers. These beads participate in a dynamic water cycle. You see, as lunar surface temperatures fluctuate during the roughly 29.5-day lunar day-night cycle, some of the chemically bound water can be released back into the thin lunar exosphere. This explained decades of puzzling observations. Instruments orbiting the Moon had detected subtle moving signatures of water vapor during daylight hours, but no obvious reservoirs had been identified. It turned out that the upper layer of regolith itself could store enormous quantities of water, with estimates from the Chang'e 5 samples suggesting as much as 270 billion tons of water equivalent across the entire lunar surface. For context, that's roughly equivalent to the combined annual freshwater usage of humanity multiplied many times over, locked in soil no deeper than a few meters. Yet the glass beads were only part of the story. In 2024, a team of Chinese mineralogists announced the isolation of a previously unknown hydrated crystal from the same Chang'e 5 soil. Unknown Lunar Mineral 1, shortened as ULM-1. This mineral is ammonium magnesium chloride hexahydrate. Each unit of ULM-1 contains 6 water molecules chemically locked within its crystalline lattice, making up as much as 41% of the mineral's total mass. The ammonium ion in its structure contains nitrogen, a key element for both agriculture and fuel production. On Earth, nitrogen is a staple in fertilizers and a critical component of chemical rockets, but it is scarce on the Moon. Finding a mineral that combines both water and nitrogen is akin to stumbling upon a pre-packaged survival kit. Astronauts can extract drinking water, produce ammonia for growing crops in lunar greenhouses, even synthesize fuel for return missions, but there's more from where that came. Exotic carbon and energy resources. Studies of the samples also led to the first ever discoveries of natural few-layer graphene and microscopic graphite flakes embedded in the regolith. These carbon-based materials were remarkable not merely for their rarity, but for what they implied about the Moon's early chemistry and energy potential. For decades, the prevailing theory had been simple. The colossal impact that formed the Moon, some 4.5 billion years ago, would have stripped the satellite almost entirely of volatile elements, including carbon. Yet here it was, hiding in plain sight. The graphene, a lattice of carbon atoms just a few layers thick, had been identified through Raman spectroscopy and high-resolution electron microscopy. Scientists were immediately struck by its pristine structure. Unlike terrestrial graphene, which is artificially exfoliated or grown via chemical vapor deposition, these lunar flakes had formed naturally, without industrial intervention. Their presence in the samples indicated a formation process tied directly to the Moon's volcanic and surface chemistry rather than contamination from Earth. The team, led by Dr. Chen Wei at the Chinese Academy of Sciences, proposed a radical mechanism. Ion-catalyzed reactions between volcanic gases and the relentless influx of hydrogen and other ions from the solar wind could synthesize carbon sheets at temperatures as high as 1,100 degrees Celsius. In effect, the Moon had its own miniature carbon factory, producing exotic materials over hundreds of millions of years. Graphite flakes, larger and more robust than the few-layer graphene, measure up to 1 millimeter in diameter. Their origin is likely linked to slow deposition from gas-rich eruptions that allowed carbon atoms to crystallize and settle over time. The distribution was not uniform. Only a fraction of the soil contained these flakes. Researchers were equally thrilled by the simultaneous identification of helium-3 trapped in a rare phosphate mineral known as Chang'e Y. Helium-3 is an isotope almost non-existent on Earth, but abundant in the solar wind, and when used in nuclear fusion reactions, it has the potential to produce enormous energy with minimal radioactive waste. In Chang'e 5 samples, helium-3 concentrations in Chang'e Y measured up to 50 parts per billion by weight. That may sound small, but extrapolated across the vast lunar surface, it could represent trillions of tons of potential fuel concentrated in a chemically stable mineral. Unlike surface-adsorbed helium-3 in the regolith, Chang'e Y binds it securely within a lattice, preserving it from solar wind sputtering and micrometeorite erosion. These discoveries also highlight the Moon's dynamic relationship with the Sun. Solar wind particles, primarily helium, hydrogen, and carbon ions, bombard the surface constantly, interacting with volcanic remnants to produce a slowly evolving suite of exotic minerals. The Chang'e 5 team observed that carbon concentrations were higher in regions where solar wind exposure was prolonged. Energy planners are paying close attention. From exploration to a lunar future. For decades, we studied the Moon from afar, sending orbiters and landers to skim its surface, collecting grains of soil and fragments of rock. But in the past decade, those distant observations have transformed into a new strategy. The data gathered by the Chang'e missions has been the spark igniting a new vision, a Moon that is not merely observed, but inhabited. All the aforementioned discoveries converge toward one concept that has become the guiding principle of lunar exploration: in situ resource utilization, or ISRU. Rather than hauling every kilogram from Earth, future explorers could live off the Moon itself. Picture 3D printers turning powdered lunar soil into habitats, using local carbon and silicates to build walls and domes strong enough to resist micrometeorites and temperature swings. And in the background, helium-3 lies in wait as a long-term energy source, potentially enabling fusion reactors that produce clean, virtually limitless power. To realize this vision, China and Russia have spearheaded the International Lunar Research Station, the ILRS, designed as a collaborative platform for nations and institutions to test, develop, and eventually inhabit lunar environments. The ILRS is structured around practical objectives, integrating robotics, resource extraction, and habitation trials. International partners are being invited to contribute scientific modules, habitation technology, and experimentation with ISRU techniques. The station is envisioned in the South Polar regions, where permanent shadows harbor ice deposits, and temperatures are more stable than the equatorial extremes. Here, water and other volatiles can be harvested, processed, and used as a lifeline for future crews. Upcoming missions mark the next stage of this story. Chang'e 7, scheduled for 2026, will map polar ice in unprecedented detail, using a combination of radar, spectrometers, and in-situ measurements. Its goal is to locate and quantify ice deposits that could sustain long-term operations. Then, Chang'e 8, arriving in 2028, will take experimentation to the next level, testing 3D printing from regolith, demonstrating the feasibility of constructing habitats and infrastructure using only local materials. These missions can transform the Moon from a static scientific target into a resource-rich, operational environment.
The resources are not merely scattered. They are concentrated in ways that suggest the Moon could sustain human activity if approached methodically. Water exists not only in shadowed craters, but in upper regolith minerals, and carbon is preserved in graphene flakes and graphite pockets. Helium-3 sits locked in Change Site Y, waiting to be harvested for energy. Even construction materials such as silicates, aluminum, and iron are available for turning regolith into habitable structures. By the early 2030s, the Moon could host semi-permanent stations, operating as both scientific outposts and test beds for technologies that will eventually take humanity deeper into the solar system. The ILRS, supported by Chang'e 7 and Chang'e 8 data, would become a hub where robots and humans work side by side. The Moon is awakening, not just under human gaze, but under human presence. Its frozen surface is revealing secrets that collectively redefine what a celestial body can offer. Through the careful choreography of sample returns, mapping missions, and the ILRS, the Moon is transforming from a passive observer of Earth into a partner in human expansion. It is a story that began with curiosity and observation, but it is moving toward action and habitation. The next chapter in the history of lunar exploration is about to unfold. Outro. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.